Okay, so I left you on a cliffhanger. I think we're going to try this again. Let's see here. All right. So why does each light have its own spectrum? That's where we were. We said that electrons can absorb energy and then they can't stay on a higher energy level forever. They have to let the energy go and go back to its original ground state. Okay, so when it lets that energy go, sometimes it's in a form that we can see. Sometimes it's visible light, which is, again, where you're going to get fireworks and all those really pretty colors. It's because they're releasing energy that was originally absorbed. Okay, now when electrons move back, I'm going to move my floating head here. When electrons move back to ground state, they emit energy in the form of photons. Photons are tiny little packets of light. Okay, and they have specific frequencies. Those frequencies make up their own little blueprint. Okay, and so every element, whenever it gives off a certain amount of energy, that becomes its own little spectrum, its own little spectral graph. And every element has that. It's like its fingerprint. And so what we want to try to do is figure out how would you calculate the wavelengths and frequency, because if you can use those properties of waves like wavelength and frequency, you can also calculate how much energy those waves are carrying. Okay, so that's what we want to do. Okay, and over here, this is I think this one is nitrogen, the nitrogen molecule's emission spectrum. So like into a nitrogen molecule, this is its little emission spectrum. Okay. All right. Now let's talk about how do you calculate. This is what everybody's going to be interested in because this is going to help you do your homework that I assigned last night. Okay. First of all, wavelength. Oops. Wavelength is this little upside down Y thing. Wavelength just measures the distance between like the top of one wave and the top of another wave, or in other words, from trough to trough, the bottoms of the waves. That's one wavelength, okay? We measure this in meters, okay? That's the unit that we're going to use. Frequency is designated usually by an F in some of the formulas, or this weird little Greek, or not Greek, it's Latin, like it's called a VU, I think. Anyways, this weird little V looking thing. It's the number of waves or cycles that pass through during a time period. And then energy, E, is the radiation carried by waves of different wavelengths and different frequencies. Every type of radiation will carry a certain amount of energy, and it's dependent upon the amplitude, the height of the wave. It's dependent upon the wavelength, the distance between the waves, and it's dependent upon how close are those waves together. What is their frequency? Those three properties will determine energy of a wave, okay? So, and there are relationships like the longer the wavelength is, the lower the frequency is. It's going to have less energy as those waves get spread apart. If those waves are crammed really close together, they're going to have high frequency. So short wavelengths, high frequency, high energy. Okay. So here's our formulas that we need. This first one here is C is equal to lambda times V, okay? Speed of light is equal to the wavelength times the frequency. So this is the first formula that you're going to need in order to solve problems. You just got to figure out what is the frequency of the radiation that they give you and what is the wavelength. Frequency is measured in hertz or cycles per second, like 1 over S. That's going to be frequency, either hertz or cycles per second. Wavelength is measured in meters. It's a length. Okay. And of course, the speed of light, that's going to be a constant, like 3.0 times 10 to the 8th meters per second. Okay. And then we've got this formula. This is called Planck's formula. Now, part of the formula, this first part, E is equal to H times V. V, again, is that frequency value. So E is energy. H is Planck's constant, which is a constant number, 6.63 times 10 to the negative 34th joules seconds. And then V is frequency. This will help you find energy, okay? Or you can replace this formula with this formula, H times C over lambda. So where H is Planck's constant, C is the speed of light in a vacuum, and lambda, of course, is your wavelength. These are the formulas that you're going to need in order to solve the problems 1 through 7 or 1 through 6, whatever it was.